Hey internet people, welcome to the first video on my new YouTube channel. Today I've got 4 fans designed in DFDC to show you guys. Got some pretty interesting designs made in DFDC with a modified S1223 airfoil. I made it a little bit thicker so it's easier to 3D print, but we've got the A12 X25 here, not the PWM version, but I have 2 different voltages to experiment with power supply and RPM. So just to talk a little bit about the fans here, the Xfoil results for the S1223 were a little optimistic maybe, so I have one with a boundary condition at 65 degrees to kind of ensure that, you know, we don't put so much effort into testing fans that are completely stalled out. So, and I have a swept version here as well, so there's 2 different fan geometries. One's higher pitched, one's lower pitched, and then each of those has a swept version as well. There's no sweep in the simulation, although there is a rake variable in the DFDC program, but the optimized versions here are only the straight blades, and we're just kind of experimenting with the swept version to see what that does with the fan. So yeah, I guess you can get started here on what we're going to be looking at. You got high pitch swept, low pitch swept. We're going to be looking at meters per second, decibels, RPM at 12 volts and at 18 volts. And actually meters per second was a little confusing because there was only 2 sig figs, so we're going to change that to feet per minute because that gives us 3 sig figs and it's a much smaller unit. So change that over quickly. And what we got to test here is anemometer, a cheap anemometer off Amazon if I can get it here. Turn it on, it'll be upside down. Yeah, so we got it set to feet per minute there, and that's pretty self-explanatory. There's a blow-emitron in the middle of it, and we'll get feet per second from that. Got kind of a customized shroud here. If we can give the print quality, we're experimenting with 0.8 millimeter nozzles, so the supports were kind of hard to get off at that nozzle thickness, but we're going to use this to get the airspeed measurement. There's just kind of a hole in the back for the air to escape, and it should measure things nicely, hopefully. If not, we'll find that out. We're going to use a typical dB meter off of my running cell phone, and then got an RPM sensor here as well. So yeah, let's get started. So first we're going to deal with the stock fan on there at the 2 different voltages. So let's try that out. Put the get everything front and center here, and just for testing purposes, we'll have the fan. We'll have the phone right in front of the fan there. Let's go ahead and plug in the 12-volt power supply. So you got 80 dB at 12 volts. $12.09 for RPM and 307 for feet per minute. It's at 298 and then 307. Keep switching back and forth. Let's try 18 volts. Got a new max at 83. Sounds a lot louder to me though. constant airspeed at 394 feet per minute. RPM 1789. So here's the stock stuff. Let's see how it compares. Alright, so we got the new fan installed. Took a little bit longer than I would have liked. This one is going to be the high pitch unswept version. So we're going to try it at 12 volts. Alright, let's try this again. A max of 80.3 for the noise. And that is completely borked, I think. There is nothing coming out the other side. Nothing at all. So let's see. Yep. Stopped. It doesn't have enough to push through. So it's kind of more of an impeller. We can still get the RPM though. Call it 915. And let's try 18 volts. All right, so it's actually moving some air now. We're at 259. For speed. Oh, now it's changing. Between 240 and 270. We'll just leave 259. And the RPM. I think 1260 would be fair. And there we have it, project failure at 12 volts, and we'll see how this adds up. Not too favorably to the other feet per minute. I think it's below Noctua in both cases. Let's try and see if the swept version of the same fan design is any better. Let's give it a shot at 12 volts. A max of 81.1 on the dB. Got for RPM. 937. And zero again on the airspeed. Not too good. Let's try 18 volts. .6 on dB. So we're at 278 now there. So it has improved over last time. RPM went up both with the swept version, so we'll see if it goes up in both cases. 1304 on RPM. Okay, so that's 2 finished. Obviously only useful at 18 volts. At least with the contraption I have on the back there. Not sure about what that really does to the Reynolds number. Obviously it's not like a propeller where it's in open air. You've got lots of different cases. Excuse my pun, where these fans get used. So obviously this one's not too flexible. Let's see how the low pitch version goes. Alright, so the neat thing about these fans is limiting the pitch actually increased the optimal amount of blade numbers, at least considering the simulation. So just working with these computer fans, not too familiar with them, trying to maximize thrust. I don't know if that's the best thing to do or not, but obviously the program got really carried away. Both these fans kind of increase pitch towards the tip by a couple degrees, which you really can't see. But this should be pretty interesting. So let's give it a try at 12 volts. So you got 80.4 for the maxed sound. This is the unswept version. $884. That's seems right. Just making sure not to hit the other pieces of tape there for RPM. And let's see what we got here for airspeed. So it really can't move it. It's at 0. Another 0. So that's not good. So let's try it out at 18 volts. $80 for the max dB. $12.14 for RPM. And 211 for airspeed. Alright, so we have the swept version. There's only one left to go. And we're gonna need a new piece of tape. Alright, this is our last hope. Looks good there. So here we go, 12 volts. $79.6 for max sound. 12 volts. So we finally have air movement, 173. Constant 173 feet per minute. Constant 917 RPM. So I guess that's good. Let's try it at 18. $80.6 for noise. $12.67 for RPM. It's just really low compared to the Noctua. And $2.49 for feet per minute. So, I think it's the best all-around fan. It's kind of pretty comparable to the low-pitch version. We have to get a real graph up of it. I didn't really like the sound. maybe I can go through the video and get the averages, which would be better than the spikes or the max. But we're pretty short of even the 12 volt result on the A12X25. So we got 278 max. So it's doing pretty good. So I don't know. I think I don't know if we're creating too much back pressure with this test. I don't think so. Doesn't seem like that to me. It does pretty well just by itself. I mean, I kind of think the tests are on the computer are a little better because the differences that are small can accumulate over time with heat. So I might try something like this. Put a fan on something like a Raspberry Pi. I don't really feel like messing with a whole desktop. Maybe I'll have to do that, but I think the fans definitely need to go back to the drawing board. So, yeah. Should have been a little suspicious with the tips angle at the tips being higher than the root. But I guess that's what I get for optimizing for thrust. So, I mean, I don't really know if that makes any sense, because there's a lot of, I mean, you can create a lot of thrust with a fan this size. I mean, the RPM is fixed, obviously, so I don't know what the real max is. But what kind of thrust do you want to aim for so you don't stall out your whole fan like we did here? That's an interesting question. I think we got to find a better way to optimize it. Maybe power reduction. It'd be neat to measure the electrical power being used. I don't know if anybody really cares about that in their computer, though. So, yeah, definitely back to the drawing board, you know. So thanks for watching, guys. This episode is sponsored by absolutely nobody. And I don't know. I have a lot of free designs up on Thingiverse and some designs on my website, 3dprintair.com, if you guys want to check it out. I'm still really working on that, so if you guys want to take the free stuff on Thingiverse, let me know. If you guys want me to start a Patreon with exclusives, let me know that as well. Probably end up doing something like that if enough people ask. And anyway, I hope you guys enjoyed this practice in humility. Definitely got to go back to the drawing board, figure out what Xfoil is doing, maybe try a triple variable airfoil, do something. But this is all for Major Hardware's fan competition, so if you haven't seen any of that, go check out his channel, Major Hardware at YouTube. Looks like I said, got to go back to the drawing board, but I'm definitely still planning on competing. Who knows, by some miracle, maybe these fans will do better on a radiator, but I'm definitely going to try to improve it some more. You know, put a lot of thought into it. Didn't really necessarily pay off too much, but just going to try it again, figure out what's wrong, and I'll have the airfoil coordinates and the down in the description, and might put the fan designs are out there on Thingiverse already, and I might keep the DFDC inputs on Patreon if I end up doing that. I don't know. Let me know what you guys think in the comments. Really, the guys that made to the end of the video, thanks for watching, and be back next time.